You can see from the title that we're going to start a new topic. This is the one that I've been sort of threatening to start for a while. Basically starting to talk about schema design and how you might go about it and various aspects of that whole problem. Now, of course, anything that requires a database typically already is going in a direction that's going to be pretty complicated. There's really simple solutions for storing information, like if you have a small application, but then once you get up to a certain size and you start saying, oh, I need a database, typically that also means you have multiple users accessing your system at the same time, so you have concurrency issues to think about. A lot of times, if you have multiple users accessing your data, you have security and role issues to think about. So there's a lot of different things that start to show up when you get to the level of an application that actually requires a database as part of the system. Now we're going to focus primarily on the database side of things. It would be really great to run you through how you design an application in the first place, but I think that's probably a topic better suited for a different class that we don't really have at this point. But anyway, design areas. So you have the schema itself, obviously. You go through the schema design itself. You have to figure out what programs access the data, modify the data. Maybe it's just one. Maybe it's a website that you develop and it has different components to it, like an administrative area and a user area, and users may have different things that they can do with the data and so forth. Then you can start thinking about security constraints and so forth. So there's a lot of stuff you can look at. What you notice when you design these systems, like let's say you're the database expert that comes into the situation to design the schema, and you're going to do all your magic and apply all the normal form knowledge that you gain and all of that kind of stuff. Well, unfortunately, that doesn't help you if you don't understand the problem that people are trying to solve. Because again, just like when you write a program and you create abstractions, data types in your program, and those are abstractions of some real world thing that you're trying to model, or maybe aspects of a problem that you're trying to solve with the computer. When you create a database schema, it's an abstraction or it's an approximation of what you're trying to model. So you're trying to create a supermarket database or something like that. So then you have to ask the question, do I have discounts for some customers and not for other customers? Am I going to have different prices for products in different areas? Am I going to have products not available in some? So you start asking all these questions, and clearly a domain expert is the one who should be answering those things. So it's like typically you get this collaboration between people who understand the problem and people who understand the technology to try to solve these kinds of system design issues. Okay, so you collect user requirements, what needs to be represented, like, oh, I have a company and it's a large company, so we definitely have employees with the same name, that kind of thing. We need to be able to distinguish between them, maybe have a picture as well. Operations to perform on that information. So what kinds of tasks will the database need to support? It turns out that this actually has a pretty big impact on the design because obviously if you have an operation you want to perform, and it's really complicated because that information is spread across 19 tables or something like that, then that's going to be a drag. And so you want to try to think about a database schema design that will allow you to do the operations you need to perform relatively easily. Okay, that's a big aspect of why you might choose one design over another. Okay. So yeah, conceptual schema, this is what we're aiming at. This conceptual schema is kind of like a sketch of what your program might do. Or it might be like pseudocode, where you've just sort of outlined the way that an algorithm might operate. So a conceptual schema is sort of at this high level where it's easy to revise, it's easy to consider, and you can take that conceptual schema and evaluate it against the operations that you need to perform on the database. Now, like I say on the slide, the best conceptual schemas follow a specific data model. Remember, we talked about data models in the very first week of lectures, where we said a data model says, what am I allowed to actually represent? What kinds of relationships? What kinds of values? How do they interact? What kinds of constraints can I impose? So if we follow a data model in the conceptual schema, then we start getting a lot of power out of doing that. And I'll show you momentarily. Yeah, it's represented graphically because why not use our fancy brains and our fancy eyeballs to be able to evaluate things. Okay, as far as the specific operations, I've kind of mentioned that a few times now. Typically what we do is we collect those into some kind of functional requirements document. And it's kind of funny the first time you hear it, but functional requirements are things that you would like to do. Okay, so those are functions or features that you'd like to be able to implement. It turns out that there's a whole other area called non-functional requirements, and it's not that you're requiring the system to be non-functional. Rather, what it means is that you may have other requirements for the system that are performance requirements or reliability requirements, things like that, throughput requirements. They're not saying what you need to be able to do, they're saying details about how the system should be able to operate. Okay, so but the functional requirements are pretty important to actually being able to evaluate whether or not the schema is any good. Okay, like I'll give you an example. Not uncommon if you're using a website like Amazon or Facebook or something like that to change your email address. Okay, that's not such a big deal. But I can tell you, since I was around when the internet and the World Wide Web kind of became a big deal, that people would design websites and you couldn't change your email address. Like, well, that's not very useful. I'm going to change email service providers, and now I have a whole new email address, and I would have to create a new account on this other system, on this website. So that's an example of, maybe that should be a functional requirement. Users should be able to change their email address without, causing the system to freak out. And so that would be a great example of a functional requirement. And you just evaluate that against your schema design. Okay. All right, so that's just one simple example. There's a lot of other directions you could go in exploring this. In fact, there's really good books on this kind of stuff. So that's it's one of those things. It's like trying to teach people how to design programs or how to structure programs in CS1. Right? I mean, it's a very broad topic, and you can only scratch the surface in a class like that. Similarly, in this class, we only spend a few short weeks talking about this, and it's too bad. It's one of those things you need a lot of experience to really understand the patterns that you'd like to follow. But we try to show you as much as we can in this class. Okay, so we have a conceptual schema, functional requirements. We verify them, and we can do that partly because we understand the data model of the conceptual schema. The next step is to take that conceptual schema and turn it into an implementation data model. And this is really cool. Like, the reason why we can turn the schema that we specified in this conceptual model into an implementation model is because we have some formal specification of what the conceptual model means. Okay, so when I draw this kind of diagram or this kind of picture and I underline this stuff or I put a star by this other stuff, it means something that I can use to generate SQL, which is pretty neat. And so, I'm not going to talk about that quite yet. It turns out that there's a lot of commercial tools that are able to do this kind of thing. And so you don't have to go very far. You could just search for entity relationship model or entity relationship diagram on the internet, and you'll find a bunch of tools that actually allow you to model schemas. In fact, I'm pretty sure that MySQL Workbench is able to do this at some limited level. But there's very sophisticated tools that you pay a lot of money for to be able to model schemas at a conceptual level, then push a button and it spits out SQL. In fact, even like Visio can do that because Microsoft Visio is designed to work with Access. Okay, so that's not too much of a surprise. And SQL Server and other tools that Microsoft produces. Okay, finally, physical design. Remember that the idea is that since we are working with SQL as our goal, the implementation data model will still be at that logical level. So we can actually be pretty well insulated from physical design questions. But you always run into this kind of thing. My system scaled because my website was wildly popular. And now I need to figure out where to put indexes. Or I need to figure out, like, how do I partition data across multiple servers so that I can spread out load and I can answer people's questions quickly enough to keep them coming back. Stuff like that, right? I mean, that's the kind of design, these are the problems that you like to have. Like this is, if you have unhappy customers, at least it means you have customers, right? And so you can figure out how to make them happy. But sometimes physical design, that'll emerge a little bit further on down the road as you scale your system. Okay, any questions about any of this at this point? All right, hopefully all pretty straightforward. It turns out that not all of the design choices you have will necessarily have the same impact. And this is one of those things, like a lot of people when they start out programming or start out doing software design, they don't like to spend very much time up front thinking and designing, because thinking and designing doesn't look like work. And a lot of times you kind of see this in commercial settings. You try to avoid companies that behave like this. But you want to spend time up front designing and thinking, because that means that you get to throw away a whole bunch of potential avenues that would lead to dead ends. You would like to choose paths of development that actually are going to pay off in time. Physical level changes tend not to have much of an effect. And this is because of the relational model, and because of SQL, we try to isolate those kinds of changes as much as possible from the way that the database application actually works. So for example, I decide that I'm going to set up temporary storage on an array of solid state drives. Or I have these tables that are used by all kinds of systems, and so I want to replicate them everywhere. That's a kind of change that doesn't really have any effect, because it just is going to make things faster. Everything's going to keep doing the same kind of processing, but it'll just be much, much faster. But when you start changing schema, you add columns, or you change the meaning of columns, or you remove columns, or you add tables, or you refactor information so that it's spread out across multiple tables when maybe it was just in one table before, that actually starts to have a profound impact on what you're able to do, and it touches a lot of the application state. Okay? So this is why it's important to spend time up front actually designing your database schema. Okay? I don't think this is necessarily something that would surprise any of you. You've probably all had enough experience with problem solving that you've seen this kind of thing before. Now, since there are a lot of ways of representing information, there's two main questions you kind of end up asking yourself when you're designing a database schema. The first one is, do I have extra redundancy in how I'm representing information? Okay. You could probably think of well, I'm not going to use that example because it actually factors into the second question a lot as well. But unnecessary redundancy is if you have to store the same piece of information or the same fact in multiple places in your database just to satisfy the constraints of how you've designed it. Okay? We'd like to have each fact appear in only one place. Like accounts, we're actually going to look at this when we start getting into the next topic. What if you had a situation where you had to represent accounts multiple times in the account table? That would kind of be a drag, because each time you have an account number, you have to make sure you have the same balance. Like you can't have the same account number with different balances. That would be a disaster. So we want to avoid unnecessary redundancy because it helps us maintain the correctness of our data much more easily. If every fact is in one place, then it's a lot easier to keep from screwing things up. Okay? So that's the goal. You'll also notice that not everything can appear in only one place, like accounts. I talked about accounts. Maybe it's a big problem if the same account balance, the same account's balance appears in multiple places, but the account number may appear in multiple places, because that's how we represent relationships. So you can see that some redundancy is necessary, some redundancy is bad, right? And so what we really want to try to shoot for is eliminating unnecessary redundancy. And we'll talk a little bit about what that means when we get into the next topic. The other thing, which is really obvious, is an incomplete representation, i.e., there are facts that we need to represent because of what we're modeling, but we can't actually represent them in our database design. That would be disastrous as well. And so the example that I was going to use, because like having customer name as a key is a really bad idea, kind of because of both of these. We don't want to repeat customer names all over the place because that's a drag. We know they're going to take up a lot more space than like a 32-bit number if we just assign a 32-bit number to customers. But then we also have the problem of incomplete representation, which is if we have the same customer name, we have customer name as a key, then if two different customers have the same name, we can't represent that. That's clearly incomplete, so that's problematic. Okay? So those are the two major things we try to steer clear of when we do database schema design. Okay? Now, besides those two things, let's say you do a perfect job of avoiding those two things. And I know because I've designed database schemas that avoided those two issues, but then they had a whole bunch of other issues, so they ultimately ended up not being used. Okay? And so that's where you evaluate it against the operations you need to perform. Like, how hard is it to access useful information? Well, if it's a giant pain and it's really slow, there was one time I was working at a company, and they happened to have a particular database design that made it unbelievably slow to retrieve the information they needed from the database. And so they had to completely redesign the schema. So even though it represented everything they needed, it was just hideous. Okay? How hard is it to update the system, performance, and scalability considerations? So those are the kinds of things that you have to consider. So this is why I like this. It's kind of like programming. It's kind of like trying to write a really fast program, in fact. Okay? Let's say that you need it to be really fast, but you also want to make sure it's easy to maintain. So you have practical considerations, and you have aesthetic considerations. And the whole idea of designing real-world systems generally ends up requiring a balance somewhere in between those two. You've got to figure out the right balance. And so you may have a design that's very clean and from a theoretical standpoint is just really pure. No repeated information anywhere, but it's really slow. And so you have to relax some of those constraints and end up with a system that has some redundancy, but it ends up being a whole lot faster, and then customers are happier. So this is the challenge that you kind of face when you design databases and also a lot of other systems. Okay, so that's the prelude, if you will. That's the sort of introductory material about this whole database schema design question. What we're going to do now is start talking about the entity relationship model, which is actually really common, although I have to tell you that it's just like a language with many dialects. There's a lot of different variants that you see with the entity relationship model. So what I'm going to show you is sort of a nice generalization of it, and then in a few lectures we'll go through some special cases that you frequently run into. But this is a nice high-level abstraction that's really fantastic for designing database schemas. And I've actually really enjoyed using it. So yeah, you can have complex schemas. There's a lot of abstractions, in fact. There's hierarchies of types, there's aggregation, there's a whole bunch of other nifty things that you can do with it. Okay? And the nice thing is that since it is well specified and it has a lot of similarities, in fact I'll point them out as we go through because unfortunately the material in this lecture is kind of boring. I think it's partly because I decided to follow the way the textbook presents it as opposed to coming up with my own way of presenting it. And so I'll try to point out some of these details of how the entity relationship model maps to the relational model very easily. Okay? So this is really cool, and that's why there are tools that can do this for you. Entities. So it's called the entity relationship model. It sort of indicates that the two main things that you have in the model are entities and relationships. So an entity is any kind of thing that you might want to represent. Okay, some of you have laptops. A laptop is a thing. So that would be an entity in the entity relationship model. Okay, I'm trying to come up with other things. A book, a battery, this water bottle, which is way too old. I need to get a new one. But anyway, you have like all these things. Those are examples of entities. And entities have attributes, some things that we want to keep track of for each entity that describe that entity. So it's like if you took all of our laptops, you could say, it looks like Apple is well represented today, it looks like. So you could say, like, what kind of Mac is it? You could say how much memory is in it, what kind of storage, what kind of processor. Those would be attributes. And probably every single one of our computers has different values for those things, but they all have the same attributes. Okay, so those are examples of attributes for an entity. Now, if this is sounding a lot like a tuple and values in a tuple, that's exactly right. That's exactly the way that entities map into the relational model. An entity set is just a collection of entities. So hopefully this is starting to sound like a table or a relation. So an entity set is basically you have a named collection of entities that all have the same set of attributes. So they all have the same set of characteristics that we're interested in recording about them. And so you go to carmax.com or you go to some car dealership online, you can imagine they're going to have a database. You can think of cars as being entities. So there'll be some, what cars do we have entity set, and it'll say, how many wheels or what kind of engine or who makes this car or so forth. Okay? So that's an entity set. And so entity sets correspond to relations, and the set of attributes that an entity set has correspond to the schema of the relation. Okay? So that's the idea there. Entities have attributes, blah, blah, blah. So this is basically identical to the way the relational model works. That's part of why this is kind of a boring lecture, because we do cover a lot of ground that we've already covered. But again, you can see the similarity to the relational model. Attributes have names. They have domains. Null may or may not be part of the domain of an attribute. Okay. You can think of other characteristics that you might want to define for attributes, like what is a key, and so forth. So we're going to get into all of that stuff. The entity relationship model has a lot of overlapping concepts with the relational model. And like I say here, entity sets, each entity appears once. Okay? It's a set. You see set is right in the name. And so each entity is going to only appear once. So you can imagine that every entity is going to have its own unique set of attribute values. But every entity in the entity set shares the same attributes that all the other entities in the entity set do. Okay, does that make sense? Hopefully everybody's got that concept. All right, here's how we diagram it. Customers. These are the things we might want to record about a customer, and we just draw a box. The name is at the top of the box, and then the attributes go into the box, the bottom half of the box. The rest of the box. Okay? So that's nice and simple. I really like this notation, and you'll see me rant about it in a few lectures, because this is very similar to what we do in the real world. It turns out that all database textbooks seem to choose a horrible way of representing this stuff, where it's like a bubble with customer in it, and then that bubble has bubbles hanging off of it. And I'm like, nobody does that in real life. Why are you doing that? Why are you teaching database students that stuff? So I like that they upgraded to this. I can't remember if it was in the 6th edition or the 5th edition of the textbook, but now it actually is the way that people do it. So that's really great. Okay, relationship. So this is basically an association between two or more entities. Okay, a bank loan and the customer who owns it, or if you will, since we've been talking about, real world examples sitting in front of us, the laptop and the person who owns it. That would be a really great example of a relationship. Okay? Now, this is where it gets a little bit confusing, because we can have a whole category of relationships, if you will, or you can have a whole collection of relationships. Like that this laptop belongs to me, and that laptop belongs to you, and that laptop belongs to you, and so forth. Like those are all individual relationships, but they all involve a laptop and a person. Right? So then we can collect those relationships together into this thing called a relationship set. Okay? So it's a named collection of relationships of the same type, or involving the same kinds of entities. We extend this idea and we say a relationship set relates entities in entity sets. Okay, so we start connecting these ideas up. Okay. Here's the formalism. It gets a little bit annoying, but so a relationship set involves some number of entity sets, at least two, because it doesn't make, well, I guess it could make sense to have an entity set related to itself, but then it's sort of still participating in the relationship set twice. But anyway, so we have at least two entity sets participating in this relationship set. And so we have specific relationships. We call them relationship instances, in fact, where we have some collection of entities, one from each entity set participating in the relationship set. Those entities comprise the relationship. So like the fact that this laptop and me have a relationship means that, I'm trying to think of a good way of describing it, but that would be one relationship instance in the relationship set relating laptops to owners. Okay? That's the idea. Okay? All right, so yeah, we say entity sets participate in relationship sets, and then specific entities participate in relationship instances. So this is just notation or terminology. So we just have to make sure we use the terminology correctly, because this is how people describe stuff. So again, that laptop is a specific entity. It may participate in or it may be a part of the laptops entity set. And then I'm in the people entity set. And then there's a relationship set. And a specific relationship instance relates that laptop to me. That's the idea. Okay? Customer and loaner entity sets. This is why we like the schema that we use, because it comes from the entity relationship model, and so it's very easy to understand. So customer and loaner entity sets, and then you have specific customers, which are entities. Loan, yeah, so you have specific loans that are entities in the loan entity set, and then borrower relates customers to loans. Now, the one thing about this is you'll notice we keep using the term set. So we have entity sets, we have relationship sets. So what we're saying, for example, is that borrower can only contain one relationship between Jackson and L14. Okay? We can't have Jackson and L14 appear multiple times. We're allowed to have Smith and L14 as well as Jackson and L14 because they're different relationship instances. They relate two different entities. Okay? We can have Jackson and L19. That would also be fine. But we can only have one instance of the relationship Jackson and L14. So that's what we mean when we say it's a relationship set. Okay? All right. You have roles. So what is the role in the relationship? Well, the main reason that this is important is that rarely the entities participating in a relationship, the role is not entirely obvious. Okay? So a purchase relationship between a product and a customer. Okay? So-and-so bought this thing. Like if you go to software.caltech.edu, it remembers what software you've purchased, right, to get as a site license or something like that. So the role is obvious, right? The product is the thing that was purchased, the thing that you wanted and decided to get. And then the customer is the one who decided to do that. Okay, so that's not a big deal. So you don't really say anything about them. But sometimes you do have situations where the roles are not obvious. And so frequently this is situations where an entity set is related to itself through a relationship set. And employees are a really great example of that. So employees and managers, you'll have one side of that relationship, which is I'm the one being managed, or I'm the employee, and the other side is I'm the manager. I'm the one who has to make sure that they're doing what they're supposed to do. Okay? So that's an example of why we might want to specify the role in certain circumstances. Okay? So you might have something like this, manager and worker, or employee manager, something like that. I mean, it's pretty easy to do. Okay, any questions about any of that? Again, I hope that it's all really clear, because this is the conceptual model that we'll be working with for a couple of assignments. And you'll have to do some schema design on the final exam too. Nothing usually terribly complicated, unless I get carried away with myself. But generally, if these ideas are straightforward to you, then that's a good sign. Okay. One of the fun things about the entity relationship model is that relationships can actually have attributes. Now, the thing that's unusual about this is that remember that I can have only one relationship through a particular relationship set between a pair of entities or some number of entities. I can have attributes that describe that relationship, but notice I say here they don't identify the relationship. That's because the relationship is identified by the entities that are participating in that particular relationship. For example, laptops, again. Every single one of you, as well as I, have a date on which we got the laptop. It's the first moment in time that we actually had it to start using it. So you could think of that as a descriptive attribute, but it doesn't identify that particular relationship. What identifies it is that the laptop is this one and I'm me, and there's a relationship there. Okay? Because you can have multiple people who got laptops on the same date. No reason why that should be disallowed. Right? Apple sells a lot of laptops. So descriptive attributes describe interesting details about a relationship, but they don't identify the relationship. It's identified by the entities participating. So a relationship between a software defect and an employee, you might have a date assigned, so that just describes the start of that particular relationship instance. But it's the employee and the bug that identify the relationship. Okay? They don't, they identify the relationship. The date just simply describes it. Okay? So this is kind of an interesting thing. Already you can clearly see that we've taken a step up the abstraction hierarchy because we're distinguishing between entity sets and relationship sets, and that there are different kinds of ways that we might relate values in different tables. Okay? Because it turns out that entity sets map to relations. It's really obvious how entity sets map to relations. Relationship sets also map to relations. But they have a kind of slightly different behavior. Okay? So you can see that this is a higher level of abstraction. You could think of the relational model being like C++, or C, if you will. And entity relationship model is like Python or Java, something that's higher level and allows a little bit more abstraction. Okay, specific relationships are identified only by the participating entities. This is what I was telling you. So, and this is like the real crucial detail for understanding this. Descriptive attributes, you can have the same value on different relationships in that relationship set. So if you can have the same value for different relationships, then clearly it's simply descriptive. It's not identifying. Okay. All right. Let's see. Entities in an entity set must be uniquely identifiable. I'm not sure if I actually talked about that very much yet, so I'll try to spend a little bit more time talking about this. Okay. Yeah, this is basically saying what I was saying before. Jackson and L14. We can only have one instance of a relationship in borrower that has Jackson and L14. We could also have Jackson and L19. We can have Smith and L14. But there can only be one instance of Jackson and L14. Okay, that's all we're saying here, except this is more generalized. Does that make sense? This is one area where sometimes people struggle a little bit with understanding the entity relationship model. Hopefully you won't have too much difficulty with that. Okay, 99% of the time you will design relationship sets that only relate to entity sets. Why? Because they're easy to understand. They're really comprehensible. Rarely you will find that it is useful to have 3 entity sets participating in a relationship set. If you have more than 3, you may be doing something wrong. So that's kind of the important detail there. It actually turns out that a lot of the tools, like there's this whole category of libraries and tools called object relational mappers. Has anybody heard of an object relational mapper before? If you've ever used anything like Django or Hibernate, Java EE, any of that kind of stuff, SQL Alchemy is another Python library that does that. They're object relational mappers. Frequently, those libraries can't handle relationship sets with 3 entities participating in each relationship. Okay. Anyway, so you do have sometimes ternary relationship sets. So we call that the degree. So degree 2, very common. Degree 3, uncommon, but does happen from time to time. Like the problem that I give you on assignment 5, frequently people use a degree 3 relationship set as part of their solution. Okay? But it is easy to get carried away. You don't need these very often. Degree 4, like I've never seen it. Okay, the way that you diagram a relationship set is with a diamond. Okay, so you can see here, again, hopefully this is looking really familiar because this is a way you could diagram the bank schema that we've been using all term. You have customers, and we know that maps to a table. We have loans, that maps to a table. And we have borrowers, which relates customers and loans. Okay, and then we've just added the descriptive attribute access date, just for fun. Okay, so the relationship set is a diamond. Participating entity sets are connected by solid lines. That's pretty important. Again, sometimes when students see this stuff, they think, oh, well, I'm just going to use this kind of line, or I'm going to use that kind of line. It doesn't really matter. But it does, because when you draw these diagrams, it's really valuable to have an agreed upon way of understanding them and interpreting them. That's why things like UML are super helpful, because everybody's decided this is what diagrams mean. And that way, if you follow the spec, then everybody will understand what you're trying to say. And so it's just like using terminology correctly and so forth. So diamond, descriptive attributes can be hung off of there. Now, usually, if you had multiple descriptive attributes, you would just have them all listed in the one box. But the box is connected to the diamond with a dotted line to indicate that these are descriptive attributes, not another entity set. Okay? Make sense to everybody? All right, easy enough. Attributes themselves can vary in a lot of useful ways. Like we want to have a lot of abstraction capabilities in how we design things. And so we have a particular domain for each attribute. There's basically 3 dimensions that you might consider. One is it simple? Let me see what I have here. Simple or composite? Yeah. So simple is just some atomic value. Like name would be a great example, or last name, or address, that kind of stuff. Composite attributes have components, and so they can be heterogeneous. That's perfectly fine. So you can have different types of components. That's perfectly allowed, and you can reference the subparts individually. Okay. Then you have single-valued attributes. That's what we've been using all term. Right? So customer ID, you only have one value. Customer name, I only have one value. But then in the entity relationship model, you can also have multi-valued attributes. So you can say customers can have 0 or more phone numbers. So now I have a set of phone numbers that I can associate with a particular customer. Okay? So this is really nice. Then you have base attributes, which are like base relations, because they're actually stored values. Okay? And then you have derived attributes, which is something you might compute from base attributes. Okay? So the example that is very common is to have birth date. That's a base attribute. And then I can compute age from that at any point in time. Okay? So this is the way that we diagram these kinds of things. This is an example of simple and composite attributes. So customer ID is a simple attribute. It's atomic. And then you might have name be a composite of first name and last name and middle initial. Okay. I know that doesn't work everywhere, but pretty common in Western databases. Address, same thing. Well, I might break that down in a particular way. Okay. So then address is an attribute, but it's a composite. It's made up of multiple components. Okay, phone number. Remember we said I'd like to be able to associate a set of phone numbers with a customer. So I can just put the curly braces around it, and I end up with a multi-valued attribute. And then here are the other examples that I gave you. Okay. Birth date, well, that's still a base attribute. And you know what? It's single valued and it's simple, using the terminology we've been using so far. And age is a derived attribute. Okay? It's also a simple attribute, and it's also single valued. Okay, but it's kind of like a function, right? It's kind of weird. Maybe if we were following JSON or Python or some other thing like that, we just put it in square brackets for multi-valued, and but the parentheses kind of indicate that it's a function of other things. Okay, questions? Alrighty, so that's that. Those are the attributes, the ways that we basically indicate attributes in entity relationship diagrams. That's what we'll use this term. Different tools have different ways of doing this kind of stuff, but that's a nice, simple, general approach. Okay, so we can have different kinds of constraints. It turns out that you can actually really constrain entity relationship schemas in a lot of different ways, which is great because you can try to design a database that can't store invalid information. That's what we would love to have. So there's three kinds of constraints that we're going to talk about: mapping cardinalities, key constraints. Now, key constraints are just like in the relational model. You have some set of attributes that's a key, so we'll talk about that a lot next time. But then the other one that you can have in the entity relationship model is participation constraints, which is basically, do you require every entity in an entity set to participate in a relationship set or not? So we'll talk about all of these different kinds of constraints as we go through this. Okay. So the one thing that you'll notice, and I actually wrote up a document. Where did I put that document? I wrote a document that basically talks about these different kinds of constraints. Some are easy to enforce, like the database is really good at them. Key constraints are an obvious one. Well, I just do like primary key, right? And then the database will enforce it for me. But then some of these are difficult to enforce. And part of learning the entity relationship model and part of learning schema design is understanding what parts of this are easy to do and what parts are difficult to do. All right, mapping cardinality. Basically, when we have a mapping cardinality, we're answering the question, or we're specifying how many entities in one entity set can participate with a particular entity in another entity set, and vice versa. Okay? How many other entities can be associated with an entity via a particular relationship set? Okay? Again, you can think of the laptop owner question. How many people own a particular laptop? Well, the way that I work with my laptop, I'd like me to be the only one who owns it because I do a lot of work on it. You know, my wife has her own laptop, and I'm perfectly fine with that. You know, we can each have our own laptop. So that's an example of a mapping cardinality that you can actually model. Okay. At the same time, I have a bunch of computers, so I might have relationships with 5 computers, but then each computer I want to only have a relationship with me. So that's a great example. How many customer entities can the borrower relationship associate with a single loan? How many loans can borrower associate with a single customer? How do banks work? Can I take out a joint loan with other people? Okay. Like my mortgage. My wife and I are on the mortgage together. It's a joint loan. Can you have a customer with multiple loans? Okay. So these are the kinds of questions you ask, and you go talk to the domain expert, and the domain expert says, yes, we would love it for multiple people to have joint loans. And we would love it for one person to have multiple loans. So you get those kinds of questions answered, and then you can figure out the mapping cardinality to enforce in the schema. Okay? Yeah, it's also called the cardinality ratio, blah, blah, blah. Okay, so here's examples of mapping cardinalities. You have 2 entity sets and a relationship set R that relates entities in A with entities in B. One-to-one mapping means that any entity in A can only have one relationship. So it can only be associated with one entity in B. And vice versa. A given entity in B can only have one relationship with some entity in A. Now that wasn't precisely stated. The slide is much more precise. We're saying the mapping cardinality is about the maximum. Okay? An entity can participate in at most one relationship. So that's why you can see that B3, for example, has no relationship. That's fine. 0 is less than 1. But B4 can only be associated with at most one entity in A, and so B4 and A3 are currently associated. Same thing with A1. It has no relationship through R. That's perfectly fine. The maximum is 1 in a one-to-one mapping. All right, any questions about that? Cool. All right. One-to-many. Okay, so an entity in A is associated with 0 or more entities in B, and each entity in B is associated with at most one entity in A. So this would be an example of this picture. Okay, we have A1 through A3. A2 has no one, and that's fine for A2, because again, this is about max, not min. A1 is associated with 3 entities in B. Each one of those entities that A1 is associated with is only associated with A1. So entities in B can only be associated with at max one entity in A. All right? So that's one-to-many. Many-to-one is just this in reverse. And so that's why a lot of times when I talk about one-to-many and many-to-one, you kind of need to say what direction you're going. Like one-to-many from A to B or something. You need to have some way of clearly stating this is the many side and this is the one side. So just be aware of that. Like you could describe this as a one-to-many, or you could describe it as a many-to-one. You could do that in either direction. All right, many-to-many. This is the fun one. This is borrower. Remember, we're talking about loan and customer. Well, borrower is this kind of a relationship. Many-to-many means that any given entity in A can be associated with 0 or more entities in B. So A1, for example, is associated with B1 and B2. That's no problem. And then the same thing is true for B. Any entity in B can be associated with 0 or more entities in A. And so it's really fun. A1 is associated with B1 and B2, but B2 is associated with A1 and A3. No biggie. That's the way that many-to-many mappings work. All right? Does it make sense? All right. So what is the most appropriate for a given relationship? Well, again, this gets back to what are we trying to model? And you could use many-to-many everywhere, but that's not sufficiently constrained. Like, again, if I was modeling people and laptops, maybe there is some situation, like a family computer. Everybody uses the same computer at home. But with the advent of, portable computers and powerful portable and cheap powerful portable computers, it's not so necessary anymore. So you could say, well, what do I really want to model? Okay. So yeah, you want to constrain the mapping cardinality to reflect what should be allowed, because then the database will enforce this for you. It turns out that mapping cardinalities are generally really easy to get the database to enforce. The database is good at enforcing anything that can be rephrased as a key. And it turns out that mapping cardinalities can be restated as keys. And because of that, we can get the database to do it for us. All right? Let's see, borrower. So I'm going to just go through this, but you all will understand this. One-to-one mapping, if you had a one-to-one mapping between customer and loan, that would be a drag because each customer can only have at most one loan. Each loan can only be owned by at most one customer. Okay? So that doesn't make any sense. That's not the way that the world works. One-to-many. Well, now it's a little bit better. Customer can have multiple loans. Customers can't share loans. Again, that's kind of a drag. Many-to-one. Customers can only have one loan, but a loan could be owned by multiple customers. So again, it's like really weird. I can have a joint loan, but then that's my only loan that I can have. So the real world is customer can have multiple loans, and customers can share loans as well. Okay, so that's going to be the typical way that things work. Okay, so this is the kind of analysis you go through, and you sort of say, what are the constraints I'm trying to model? How do I actually satisfy those constraints? What constraints am I trying to model? Can I actually impose those constraints on my schema using mapping cardinalities, or keys, or participation constraints, which we'll talk about next time. Okay, any questions? Alrighty. So yeah, oh yeah, last thing to talk about. I guess we'll get through this really quickly. The way that you diagram mapping cardinalities is by putting arrows on the ends of these lines. So when you put an arrow on a line, you're saying one. It's like it's pointing to one entity. But if it's a line without an arrowhead on it, then you're saying many. Okay? So this is literally diagramming that there's a many-to-many mapping between customers and loans through borrower. Okay? If we wanted to do something dumb and use one of our other mapping cardinalities, so we have a bank that doesn't work very well, this is the way that you would do it. You would have an arrow on the customer side, and the way to think of this is that if you're standing on the customer side and looking at loan, you can have many of those. You can own many loans. But if you're standing on the loan side looking through that relationship set at customer, it goes to one customer. Okay? That's the way that I reason about it anyway. You may find another way that makes sense to you. Okay? But a loan is owned by exactly one customer, but a customer can have multiple loans. Okay? So that's a one-to-many mapping. This would be a one-to-one mapping. Arrows on both sides. You stand on the loan side, you look through the relationship set, there's an arrowhead on the other side, so you see one customer. You stand on the customer side, look through borrower, there's an arrowhead on the other side, so you see one loan. Okay? That's the way that you would diagram this stuff. Okay. Any questions? We're done. I'll see you next time.